Here we are given a third order differential equation, and we are asked to linearize the equation for x near 0. And we are going to follow exactly the same steps as before. And let me just rewrite this equation. What we are given is x dot dot plus 10x dot dot plus 20 x dot plus 15x is equal to 3 e to the minus 5x. And the first step, we say that we want to find the equilibrium point and write down the equilibrium equations as well by setting, and what we want to set all the time derivatives to 0. So if I set this is equal to x dot dot, which is equal to x dot, which is equal to 0, so I just set all the time derivatives to 0. This implies that we are going to have 15x is equal to 3 e to the minus 5x. So this is the equation that we are going to look at. And step 2, we need to write down the deviation equation. This is step 2. It says that write down the perturbed equation by deviating all the variables about the equilibrium points. So our deviation equation, we want x to be x naught plus our delta x. So I'm going to substitute that into our main equation. So I can rewrite that as x dot dot naught plus delta x dot dot plus 10 x dot dot plus delta x dot dot plus 20 x dot plus delta x dot plus 15 x naught plus delta x. This is equal to 3 e to the minus 5 x naught plus delta x. And what we've learned is the derivatives were 0, and we set that one also 0, and that derivative was also 0. And the x naught as well, this x naught will be 0, and that x naught will also be 0. So I can rewrite this as delta x triple dot plus 10 delta x dot dot plus 20 delta x dot plus 15 delta x is equal to 3 e to the minus 5 delta x. And now, as we can see, this is our nonlinear part. So this part is nonlinear, and we want to linearize that part. So we move on to step 3. Linearize the nonlinear term using Taylor's expansion. So let me just... So we know that from Taylor's expansion equation, we want f of x is approximately, we linearize around x naught plus, then we differentiate our function with respect to x, and we evaluate that at x is equal to x naught times delta x. And remember our function, because this is what we want to linearize. We want to linearize the e to the minus 5x, meaning that that function, I'm just going to rewrite it here, is e to the minus 5 delta x. Then I can just rewrite that the function we have e to the minus 5 delta x is approximately e to the minus 5 delta x naught plus, then if we differentiate that, we are going to have minus 5 e to the minus 5 delta x, and we are going to evaluate that at x is equal to x naught, which is equal to 0 delta x. And if we do that, we will have e to the minus 5 delta x is approximately, so we are evaluating x naught is 0, so e to the 0, so we're gonna have e to the 0 there plus, sorry, not a plus, we're gonna have minus, so minus 5 e to the, now x is gonna be, x is equal to x naught, and we say that x naught is equal to 0. E to the 0 again, we're gonna have that times delta x. So we are going to have e to the minus 5 delta x is approximately 1 minus 5 times 1 delta x. So this equation now is what we want to substitute in our original equation. So we move on to step 4. Step 4, substitute the linearized terms in the perturbed equation. So let me just rewrite the original equation. So we had x triple dot plus 10 delta x double dot plus 20 delta x dot plus 15 delta x is equal to 3 e to the minus 5x. And we found that e to the minus 5 delta x was equal to 1 minus 5 delta x. So what we need to do is substitute that into there. So let me just rewrite that again. Delta x dot triple dot plus 10 delta x dot dot plus 20 delta x dot plus 15 delta x is equal to 3 times 1 minus 5 delta x. Then now this equation is linear. It's just now to clean it all up, and we know that let me just use this color here. We're gonna have 3 minus 15 delta x if you multiply that out, and what we are going to have is we are going to move this into here. Then I can just rewrite all of that. So we're gonna have x triple dot plus 10 delta x dot dot plus 20 delta x dot plus, now you're gonna have your 15 delta x plus, because here we had a minus, it's gonna have 5 plus 15 delta x is equal to 3, and we're gonna have now delta x triple dot plus 10 delta x dot dot plus 20 delta x dot plus 30 delta x is equal to 3. So this is our final answer, and as you can see, it does not contain any nonlinear term. And from here we can as well find the Laplace transform of this, assuming zero initial condition. Delta s to the third x. So first I'm using this big delta plus 10 delta s squared x of s plus 20 delta s x of s plus 30 delta x of s is equal to 3. And I can pull all the delta x of s on the outside, so I can have let's say delta x of s, then I'll have s to the third plus 10s squared plus 20s plus 30 is equal to 3. So assuming that we had our u of s here, then we will definitely get the transfer functions of this system, which will be delta x of s over u of s, which will be 3 over s to the third plus 10 s squared plus 20 s plus 30. You see, now we have, out of a nonlinear system, we derived the transfer function, which does not contain any nonlinear term. So meaning that if you are given any nonlinear system, you should be able to linearize it and derive the transfer function out of it.